Welcome to Lecture 12, Unit 3, and this is What is Probability? My name is Jorge, and this is for Statistics 2023. And the objective for this lesson is that we're going to go ahead and determine the sample spaces. We're going to talk about sample spaces. We're going to find the probability of an event. We're going to talk about classical probability, and we're also going to talk about empirical probability. And you are aware of what probability is when you roll a die, or when you're playing cards. If you pull out a card, there are probabilities associated with each outcome, and that's what we're going to talk about. So what's the probability of drawing an ace if you have a deck of cards, and that's what we're going to hopefully explain in this unit, which is unit 4. So some basic concepts. So flipping a coin, rolling a die, drawing an ace from a deck of cards, these are called probability experiments. And so a probability experiment is simply a chance process that leads to some well-defined results, and those results are what we call outcomes. Now, an outcome is simply the result of a single trial of a probability experiment. So a trial means if I flip a coin once, or rolling a die once, or drawing one card from a deck once. So that's what a trial is. And so if I flip a coin, there are two possibilities, or two outcomes, right? I can either get head or I can get tail. Now, when I roll a die, there are 6 possibilities, or 6 outcomes. I can roll a 1, a 2, a 3, a 4, 5, or 6. Now, in any experiment, the set of all possible outcomes is what we call the sample space. So for the flip of one coin, the sample space will just be head or tail. For the roll of a die, the sample space would be either 1, 2, 3, 4, 5, or 6. So a sample space then is the set of all possible outcomes of a probability experiment. And we can talk about what a set is in class during the class meeting that we'll have next week. So the first thing is, let's see the sample space. If I roll 2 dice, right? So I have 2 dice, I'm going to roll 2 dice. So what are the possibilities that I have? What's my sample space? Well, the sample space would be I can get a 1 or a 1, which is the first one. Or I can get a 1 in the first one and a 2 in the second one. I can get a 1 or a 3 and so on. All the way down to I can get a 6 and a 6. So the sample space, and then not all filled in, but you can see that there are actually 36 possibilities, right? So from a 1-1 all the way down to a 6-6, those are 36 possibilities, and that's a sample space for rolling 2 dice. So another example would be the sample space for the gender of children if a family has 3 children, right? So we're going to use capital B for boys and capital G for girls. So what would be the sample space? Well, there are 2 obvious ones, right? They can be all boys, so you'll have boy, boy, boy. All girls, only be girl, girl, girl. So the sample space for that would be 8 possibilities. So boy, 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 girl, boy, girl, boy, girl, boy, boy, all the way down to girl, girl, girl. And there are 8, so the sample space is 8 possibilities, or 8 outcomes, possible outcomes for a family if they have 3 children. The next thing we're going to talk about is what they call a tree diagram, and this is simply it's a visual representation of all of the possible outcomes for a probability experiment. And so it's an easy way to determine the sample space, and also another way to determine the probability of certain events within that sample space. So let's go ahead and do a tree diagram for the sample space for the gender of 3 children in a family. Now, we did this before using a table, and we know that there are 8 possibilities, but the tree diagram looks like this. So the first one here, and this is the first child. So for the first child, the possibility is a boy or a girl. Now, once you have the first child, you have the second child. And then, so if the first child is a boy, then the other possibility for the second child would be a boy or a girl. Or if the first child is a girl, it'd be a boy or girl. So, and then this last row here, this last column, is the third child. And again, so if I have a boy first, a boy second, and then a boy third, that will give me the first outcome, which is boy, boy, boy. Or all the way at the other end, so if I have a girl first, girl second, girl third, then I would have girl, girl, girl. And if you notice, here are the same 8 possible outcomes. So the sample space is the same, whether you do a tree diagram or if you do the table. Tree diagram is a little easier, especially if you've never seen this experiment, or if you're not sure about the outcomes. So let's talk about an event. An event consists of the set of outcomes of a probability experiment. Now, an event can be one outcome or more than one outcome. So, for example, if a die is rolled and a 6 shows, this result is called an outcome since it's the result of a single trial. Now, an event with one outcome is what we call a simple event. Now, the event of getting an even number when a die is rolled is called a compound event, since it consists of 3 outcomes or 3 simple events. So now, the next thing we're going to talk about here is we're going to go ahead and talk about the 3 different types of probabilities. We have classical probability, we have empirical, and we have subjective probability. I'll go ahead and briefly talk about each one. So a classical probability uses sample space to determine the numerical probability that an event will happen. So you don't actually have to perform the experiment to determine the probability, and also classical probability assumes that all outcomes in the sample space are equally likely to occur. So for example, when a die is rolled once, each outcome has the same probability of occurring. Since there are 6 outcomes, each outcome has a probability of 1/6. Now, equally likely events are events that have the same probability of occurring. For example, again, rolling a die. So getting a 1, a 2, a 3, or 4, or 5, or 6, it's the probability of each one is the same for every single outcome. Now here, whenever we talk about these events, we're talking about a fair die or a fair deck of cards. So there's no funny business going on to tweak the probability towards one number over another. So the formula for classical probability is the number of outcomes in the event divided by the total number of outcomes in the sample space. So another way to think about it is that the probability of an event is equal to the number of the outcomes of the events divided by the sample space. And so the probability is called classical probability, and it uses the sample space S. So the sample space in this situation would be our denominator. So here's an example. Find the probability of getting a black 10 when drawing a card from a deck, right? So the first thing is you have to determine, okay, well, how many possible ways can I get a black 10? Well, if we're talking about a deck of cards, then we have the 10 of spades or the 10 of clubs, right? So there are 2 possibilities for drawing a black card from a deck of cards. Now, how many cards in a deck? Well, here are all of the cards in the deck, and there are 4 suits, right? So we have clubs, hearts, spades, and diamonds. Well, how many out of all of these cards are actually a black 10? Well, there's 2. And so 2 cards out of 52 cards in the deck. So then the probability would be 2 over 52 or 1 over 26, because we go ahead and reduce it. So again, how many ways can this particular event occur? Well, there are 2 ways, right? 10 of spades or 10 of clubs. How many outcomes are there in the sample space? 52, because there's 52 cards in the deck. Here again, if a family has 3 children, find the probability that 2 of the 3 children are girls. So let's look at the tree diagram. So look at the tree diagram, we know that there are 8 outcomes. So our sample space is 8. Well, how many of these have 2 girls? Well, here's the first one. So it's boy, girl, girl. There's the second one, which is girl, boy, girl. And then the third one, which is girl, girl, boy. So therefore, the probability that a family has 3 children and that 2 of the 3 are girls is 3/8. The next thing I want to talk about are the words and or. So in probability theory, it's important to understand the meaning of the words and also the meaning or. So for example, if you were asked to find the probability of getting a queen and a heart when drawing a single card, then you would be looking for the queen of hearts, because it has to satisfy the 2 conditions. It has to be a queen and it has to be a heart. Well, there's only one card that satisfies that, and that's the queen of hearts. So the word and means at the same time. Now, the word or has 2 meanings. For example, if you were asked to find the probability of selecting a queen or a heart when one card was selected from a deck, you would be looking for the 4 queens, because that's how many are there in the deck of cards, and then 1 of the 13 hearts. Now, excuse me, in the case of the queen of hearts, we have to compensate for the fact that the queen of hearts is a member of the set of queens and also of the set of hearts. So it's included in both sets, and therefore it's counted twice. So when we actually calculate the probability, we have to subtract that that one card, or maybe more than one card, that actually fits in both categories. So in this case, instead of it being 17 possibilities, we actually have 16. The 4 queens, the 13 hearts, and then we take away the queen of hearts. Now, if you ask to find the probability of a queen or a king, you'll be looking for 4 queens or one of the 4 kings. So that would be 8 possibilities. Now, the reason here is because there is no queen and king queen. So there is no card that satisfies both of them at the same time. So let's look at some examples, right? So we're going to draw a card. So a card is drawn from an ordinary deck of cards. Find the probability. So what's the probability of getting a jack, right? Of getting the 6 of clubs, of getting a 3 or a diamond, or getting a 3 or a 6. So there are 4 jacks, so 4 out of 52, and it reduces to 1 over 13. So the probability of getting a jack is 1 out of 13. How about the 6 of clubs? Well, there's only one 6 of clubs, so it's 1 out of 52. How about getting a 3 or a diamond? Well, let's go step by step. Well, how many 3s are there? Well, there are 4 3s, so the probability of getting a 3 would be 4 out of 52. And then how many diamonds are there? Well, there are 13, so 13 out of 52. So the next thing is, well, how many of these cards is a 3 and a diamond? And there's only one of them, so we have to subtract, and that gives us 16 over 52, which reduces to 4 over 13. Now the next one is, what's the probability of getting a 3 or a 6? Well, there are 4 out of 52 3s, and there's 4 out of 52 6s. There is no card that's a 3 and a 6 at the same time, so that's going to be 8 over 52, which reduces to 2 over 13. The next thing I want to talk about is the probability of any event. And so the probability of any event occurring is going to be between 0 and 1. And so this is denoted by the probability of event is greater than or equal to 0, but it's less than or equal to 1. Now, probabilities cannot be negative, and they cannot be greater than 1. So if an event E cannot occur, that means that there are no members or elements in the sample space, and the probability is 0. Now, if an event E is certain and the probability of E is 1 and P of E equals 1, then that means that the event will certainly occur. So, question, when rolling a single die, what's the probability of getting a number less than 7? Well, the sample space for rolling a single die is 1, 2, 3, 4, 5, 6. So the probability of getting a number less than 7 is 1, because every single outcome is going to be less than 1. The next thing is the sum of the probabilities, right? So I have a sample space, and each outcome in the sample space has a particular probability assigned to it. So the sum of the probabilities of all outcomes in the sample space is equal to 1. So let's look at rolling a die. So when I roll a die, I have 6 possibilities, right? 6 outcomes, 1, 2, 3, 4, 5, or 6. Probability of getting a 1 is 1 out of 6, a 2 is 1 out of 6, and so on. So if you look at the last row, basically what we're going to be doing is here's the cumulative frequency, if you will, right? So the probability of getting a 1 is 1 out of 6. The probability of getting a 1 or 2 is 2 out of 6. The probability of getting a 1, 2, or 3 is 3 out of 6. The probability of getting a 4, a 1, 2, 3, or 4 is 4 out of 6. All the way to the probability of getting a 1, 2, 3, 4, 5, or 6 is 6 out of 6, which equals 1. Next thing I want to talk about is the complement of an event. And the complement of an event E is a set of outcomes in a sample space that are not included in the outcomes of event E. And the complement of E is denoted by E bar. Sometimes it's also denoted by E prime, so they have an apostrophe next to it. So some rules for complementary events. So the probability of a complementary event, if there's only 2 events, is 1 minus the probability of the actual event. And the probability of the event then is equal to 1 minus the probability of the complement of that event. And also the probability of event plus the probability of the complement should equal 1. So if the probability of an event or the probability of its complement is known, then the other can be found by subtracting the known probability from 1. And this, of course, is simply if there's just two possible outcomes. So let's go ahead and find the complement of each event. So you have to be careful when you read the question, because we're not looking for the probability of the actual event. We're actually looking for the probability of the complement of that event. So the first one is rolling a die and getting a 4. So the first thing is we have to think about, okay, well, so what's the probability of getting a 4? Well, getting a 4 is 1 out of 6. So therefore, the probability of not getting a 4 would be 1 minus the probability of getting a 4, which is 1 minus 1 over 6, which is 5 over 6. The next one is selecting a letter of the alphabet and getting a vowel. So we're going to stick with A, E, I, O, U, right? So there are 5 vowels out of 26 letters. So the probability of getting a vowel is 5 over 26. So then the probability of not getting a vowel, or the probability of getting a consonant, would be 1 minus the probability of a vowel, which would be 21 over 26. The next one is selecting a month and getting a month that begins with the letter J, right? So again, how many months begin with the letter J? 3 out of 12. So the probability of getting a month that does not begin with the letter J would be 9 out of 12, or 3/4. Selecting a day of the week and getting a weekday. Again, how many weekdays in the week? There's 5, so the probability of getting a weekday is 5 out of 7. So the probability of selecting a day that's not a weekday would be 2 out of 7. Using Venn diagrams, the circle is the probability, the sample space for the probability of the event. The blue rectangle is the sample space, so the probability of sample space here equals 1, and that's going to include the probability of the event and the probability of the complement of the event, which is the blue shade. So therefore, the probability of the complement would be 1 minus the probability of the event. The next thing I want to talk about is empirical probability. Now, the difference between classical and empirical probability is that classical probability assumes that certain outcomes are equally likely. Empirical probability relies on actual experience to determine the likelihood of events. So the formula for empirical probability would be, given a frequency distribution, the probability of an event being in a given class. So here we're talking about, so let's assume that we're talking about a frequency distribution. So the probability of that event would be the frequency for the class divided by the total number of frequencies in the distribution. So it's F over N. So this probability is called empirical, and it's based on observation. So here's an example from project 1, right? So in one of the projects, the student had a following distribution for gender. So they had 10 males and 15 females. So the total number, the frequency, the sum of the frequencies is 25. Well, what's the probability of male? Well, there are 10 males, 25 in the sample space, so the probability of a male will be 2 over 5. How about female? 15 females, 25 total. Probability of a female is 15 over 25, or 3/5. Well, if you notice, if I do the probability of a male plus the probability of a female and add those up, I should get 1. And that's just a quick example there. All right, so here's another one. So empirical probabilities can also be found by using a relative frequency distribution. So here we have favorite color, right? So we have blue, pink, and red. So 6 for blue, 11 for pink, and 8 for red. So the sum is 25. So F over N is 6 over 25, 11 over 25, 8 over 25. And you add those, you get 1. And then, so then the probability of B, of getting blue, is 0.24. The probability of pink is 0.44. The probability of red is 0.32. You add those up, you get 1. So you can do either one to determine the probability of an event. Okay, so let's talk about the law of large numbers. When a coin is tossed one time, the probability of getting a tail is 1/2. But what happens when we toss the coin 50 times? Will it come up 25 times? Well, not all of the time. And this is what we call a chance, a variation. So 25 tails will not occur most of the time. So if I do experiments and I flip it 50 times and I do that 100 times, so every time I do it is 50, doesn't mean I'm going to get 25 tails every single time, right? There's going to be some variation. So, however, the more I do it, or as the sample size increases, the relative frequencies of outcomes get closer and closer to the theoretical probability value. So it gets closer and closer to the classical probability value. And the next thing I want to talk about, the last thing, is what we call subjective probability. A subjective probability uses probability value based on educated guess or an estimate. And this is just an opinion. So if I would say the probability the Yankees are going to win the World Series this year is 98%, as much as I would love them for them to win, that's subjective probability, right? So it's just based on what I feel. There's no way to quantify it. Now, there are some people out there that actually do a really good job of predicting certain events, and that's not really subjective because they're not just out of the blue guessing. They're really doing some studies and analyzing the data to come up with a final prediction, if you will. And that's the end of lecture 12, unit 3. Thank you.